Good morning, Gerson. Oh. Alrighty, let's see. We're back. It is indeed 113. And it seems that a lot of us are, it's nice to see a lot of familiar faces, I suppose. We have a few people who haven't taken 111 with me, but looks like most of you have, so thankfully this should all be pretty smooth going forward, so. Awesome. Alrighty. Let's go ahead and get started then. So, class is going to be much the same as it was last semester. We'll just have a few differences with the exams, but pretty much everything else is going to be the same. So, yeah, you guys should all be used to it. So, it'll all work out. So, we're going to start by talking about solutions today. So, we'll spend, maybe 45 or so minutes doing chemistry today, and then we'll have the last kind of 15 or so for socializing, as it were. We'll go over, the Discord stuff, just in case anyone is new, just so we can have that out there as well. So, solutions. So, these are going to be essentially homogeneous mixtures, right? Meaning they're going to be the same throughout. So we've talked about this sort of thing before. For example, we of course have our favorite homogeneous mixture, salt water, where we're going to have salt dissolved in water. So we're going to have a few vocab terms here. We're going to have the solute, which is going to be what is dissolved. And another way to talk about that is what is not the major component. For example, our salt water, the salt is going to be the solute because it's being dissolved, but it's also the part that is not the major component. So salt water is mostly water, right? With some salt. So water is going to be our major component there, and salt is not. So salt is going to be the solute for that. We're going to have the solvent be the other part. And that's going to be the thing that is dissolving the other stuff. And that is going to be the major component. So whichever component is there the most, whichever one has more moles, that's going to be your solvent. And that's going to also be kind of there can only be one solvent, where you can have as many solutes as you want. Exactly. So for our atmosphere, we have nitrogen gas would be our solvent, and oxygen and water and argon and carbon dioxide and methane and whatever. Those are all solutes there. So for example, with our salt water, we can go ahead and write that out. We have, that's going to be our solvent, and that is going to be our solute. For air, like Kevin has already said, we're going to have nitrogen is going to be our solvent, right? Because we know nitrogen is 78% of the air by moles. So we're going to have other solutes. CO2, argon, xenon, methane, I don't know, ammonia, I don't know, some helium maybe, hydrogen, sulfur dioxide, whatever. We have all these other tons of gases. So you can have as many solutes as you want, and you're just going to have one solvent. Dot, dot, dot. As, you know, at some point, you know, these become kind of trace solutes where they don't really matter as much. Like the amount of helium in the atmosphere is really, really small because helium just zips off and goes into space. Because it's so small, it can move fast enough to escape from the Earth. But something like, you know, CO2, which is a pretty heavy molecule, you know, those are more important gases that stick around. So, yes. Cool. Awesome. And so, one thing to address here is the question of why do solutions form? Why do things mix together? And we're going to have two different kind of components in there. One of them is going to be delta S, which is entropy, which we're not going to really talk about until when we get to thermodynamics. But entropy, or kind of chaos / disorder, is what the universe loves. The universe loves delta S to be positive. So that means if things are getting more disordered or more chaotic, the universe is happy. So we're going to see that solution making is something that creates disorder. So, for example, you take your nice salt crystal, which is these lovely organized sodium and chloride just dotting around, and now you've kind of thrown them into disarray, where you've now introduced water in there, and water is moving around and taking them and zipping them, and now a sodium is way in the corner. Yes. Entropy loves to be positive. Rather, the universe likes entropy to be positive. We can force it to be negative, but in general, this is going to be the main driving force behind solution formation. So, solutions are more disordered than the solutes or solvent alone. So, for solution formation, that's always going to be a positive entropy. So the universe wants us to make solutions. So just because having organized sections, if we had an atmosphere where we have a nice area of nitrogen, and here's where oxygen goes, and here's where argon goes, you know, that's totally nice and organized, and nature says, no, we're not going to do that. We're going to all mix together because I want, you know, things to be disorderly. That makes me happy, and so you can think about it that way. You can also think about it in terms of like your house. You know, it's way more easy for your house to get disorganized than it is to get organized, right? You have to put in a lot of energy to make things clean and tidy, but it takes all of 10 seconds to completely destroy things, right? Or if you think like building a building, you know, it takes years to build a building, and you can demolish it in a matter of seconds, right? So you can make it nice and orderly with a lot of energy and time, but nature says, you know how much easier it is to just make it a pile of rubble, nice and chaotic. There you go. So that's kind of the main reason that we get solutions in the first place, is because of this disorder. So that's going to be kind of the primary reason. However, we also have our very favorite thing that we've learned to dread since learning about thermochemistry way back when, is delta H, of course, which you will never be rid of. We're going to see that delta H can have some impact on solution formation as well. So, when we think of a solution being made together, right? Originally, we have solute-solute interactions. So, for example, that would be our ionic interactions within our salt crystal, and we also have solvent-solvent interactions. In order to make a solution, we have to break these, right? If we want our salt crystal to dissolve, we're going to have to break those ionic bonds, right? We're going to need to pull the sodium away from the chloride, or vice versa. And we're going to have to therefore break hydrogen bonds in between water molecules by throwing in new things, making new intermolecular forces. And we are going to therefore form interactions between the solute and solvent. Let's see if we can remember. Let's see, what was it, 5 weeks ago when we last did chemistry? If we think about the sign of delta H for these, if we're breaking bonds or breaking interactions, that's always endothermic, right? We always have to put in energy to break bonds. So for delta H, breaking those bonds is always going to be endothermic, right? And forming bonds is always exothermic. So we're going to have this kind of mixture of positive and negative things here. And so we're going to see that depending the total delta H can be either positive or negative. So just depends, right? So if the solute-solute interactions are particularly strong, then that's going to make it more likely to be endothermic, right? Or if the solute-solvent interactions are particularly strong, it's more likely to be exothermic. If we try to remember Hess's law, let's just say we have just one solute somehow. Remember that the total delta H is going to be just the sum of all of them, right? And if we think that's positive, that's negative. It just depends how big they are. And so they're going to be big or small depending on what your solute and solvent are. And so your total delta H could be plus or minus. So you will get solution formings that will be exothermic or endothermic. For example, NaOH breaking apart is highly exothermic. But potassium nitrate dissolving is highly endothermic. So you can't really tell just looking at a compound what it's going to be, but you can do it by looking at delta H values. So if you're seeing how much energy is required to break the bonds within your solutes or your solvent versus the amount of energy that you're getting out by making these new solute-solvent interactions, that's the only way to tell. So other than experimentally, of course. So for us, we just need to understand that it can be either one. So nothing too crazy here. However, yes, this is indeed welcome. If I've not had you as a student before, so awesome. Nice to meet you, Jake. So either one can happen there. Exciting stuff. Cool. So that's why solutions form. We have both a entropy term as well as an enthalpy term. Generally, the entropy is always going to be positive, which is a happy thing, but the delta H could go either way. Cool. Any questions on that? That's why solutions form. I don't expect too many questions because it's just vocab, maybe, or easy concepts. Alrighty, cool. So we have more vocab as always when we first kind of start a new topic. So let's go for it. We're gonna have a couple of new terms here. We're going to have kind of degrees of how much solute is dissolved in something. We're going to see that we're going to define a saturated solution first, whereas the solvent has dissolved the maximum of solute that it can. So eventually, if you just keep adding some salt to water, you will reach a point where the salt will no longer dissolve. At that point, your solution is going to be saturated, meaning your solvent has taken up as much solute as it possibly can. We're going to see in a little bit how we can kind of mess with this, but that's going to be how we're going to define a saturated solution. So just keep adding salt to your water. Eventually, it will stop dissolving. At that point, your solution is saturated. For something to be unsaturated, it's just not that maximum amount. So like right before you add that last bit of salt, or if you add a little bit more water to a saturated solution, it becomes unsaturated. So it doesn't have the maximum amount anymore. Now what's more interesting though, or more exciting, is the supersaturated solution. That means it has more than the maximum amount. And so you're like, what the heck? How could it have more than the maximum? Because that would be, more than 100%, which is not physically possible. But we're going to see that there are ways you can force more solute to dissolve and make it supersaturated. Supersaturated things are not stable. Let me pull up a video for you guys. That you can see what happens when you have a supersaturated solution. Let me just log in here real quick. And then we'll show you how this is going to work here. This is from my Intro Chem textbook. But let's see. Okay, I have a lovely video of what happens when we reach supersaturation. So let's see, is this the right video? Yes, it is. Okay. Cool. So here we are. This is a supersaturated solution. You can see right here it's just a clear liquid. But we're going to see what happens when I add just a little disturbance to this. If it ever happens. There we go. So you can see this has completely solidified, in fact, and you can see kind of crystals even growing up the walls of the container. Where it was a liquid before, or a solution rather, it's now solid. It's so unstable that I introduced kind of one little bit to it, and it just says, you know what, forget it, I've had enough, I'm done being a solution, I'm going to crystallize. How you can do this is something that we can look at by looking at factors that affect solubility. And then we'll talk about how you get a supersaturated solution. there's a couple of factors here that we want to deal with. And I'll ask you what to do. So you are at... Okay, Kevin already is going to just spout out all the answers, as always. But yes, that's going to be one of them. So say you are trying to dissolve some sugar in your coffee. And you want it to happen faster, right? So that's absolutely correct, Kevin. But there are a few other things. Okay, fine. We'll just do it. All right. Temperature is going to be the first one we'll look at here. Is that for solids, solubility goes up when temperature goes up. So you know that if you try to dissolve sugar in iced coffee, it's going to take a really long time, right? And maybe you're not going to get a huge amount to dissolve. But if you have hot coffee, it dissolves really quickly, right? We're going to see that typically for most solids, there are a few that are exceptions, your solubility is going to go up when your temperature goes up. Not only is this going to be the rate of solubility, but also the amount that you can dissolve. So you're going to see that you can dissolve a lot more sugar in water if your water is boiling than if it's ice water. Just physically, just because of the energetics of it. So that's one thing. We also know that surface area can affect the rate of dissolving as well. We're going to see that if we decrease surface area, we're going to increase solubility. Right? If I take rock candy and try and dissolve that in my coffee versus granulated sugar or powdered sugar or superfine sugar, we're going to see that the finer, the smaller those crystals are, the faster they're going to dissolve. If you think about like powdered sugar, that would dissolve instantly pretty much, right? Because it's the particles are so small, the surface area is so much bigger, the water can just swipe in and grab those sugar crystals and start dissolving them. Yep, you're going to have more interactions that way, exactly. What else do we have? For solids, at least. We'll talk about gases in a sec, Kevin, but just solids right here. Agitation is another one. The more you're mixing, if you mix your solution, the rate of solubility goes up. As you know, if you want your sugar to dissolve in your coffee, you better stir it, right? If you don't stir it, you're going to end up with a saturated area at the very bottom, and your very last sip is going to be disgustingly sweet. But if you mix it, you're going to homogenize the solution, right? And if you think about it physically, what's happening here is you're basically bringing in fresh water to your solute surface, right? So you've got your sugar crystal in there, and you're bringing water that doesn't have any sugar with it. And by doing so, that water is going to be more likely to grab a sugar molecule and be able to dissolve it. So you're going to kind of force, fresh water to come along and allow that to dissolve faster. So again, this is kind of stuff that you've learned in third grade, right? Where you've tried these things out. That mixing stuff will make stuff dissolve as well. So cool. Exciting. So with this, what this means, I'm going to just make two little additions here. Well, technically you are actually increasing the solubility with your temperature by breaking some of those bonds, right, that happen between your solute, or solvent things. It's more the rate of solubility with these last two. You can't really get more salt to dissolve in water if you stir it. Eventually, if you just leave your salt at the bottom, eventually it will all dissolve, but it just take a long time. So just to be a little bit more clear there. So that's how you can get a supersaturated solution, is if you have like boiling water, you add your solute in, you get as much to dissolve as possible. you make it saturated, and then you cool it down, it will have more solute than it can hold at room temperature. And that's what we saw in that video there. We had a supersaturated solution that I had boiled previously and dissolved our sodium acetate in it, and then it was supersaturated at that point and rapidly crystallized as soon as I added one more bit of sodium acetate. I added a nucleation site, but that doesn't matter. Okay, anyways, with gases, though, as Kevin has already pointed out, something to mention first, again, something you already know, if you have a cold soda versus a hot soda and you open them up, you know that your hot one is probably going to explode on you, right? It's going to fizz everywhere, going crazy, versus the cold one, which is going to probably be a little bit more tame, right? We're going to see that temperature increases lead to lower solubility. Of gases. So the hotter your solution is, the more likely your gases are going to be to kind of get out of the solution. So we're going to look at this in just a second here. So here's our lovely beaker drawing. And here are some gas particles. Let's say this is a sealed container as well, because why not? We have some gas molecules up here, and just by kind of diffusion, some of those will have gone into the solution. And so we know that temperature has a relationship with kinetic energy, right? We've talked about this, and kinetic energy is how kind of things are moving. We know that if things are happening nicely, we're going to have some gas molecules moving out of the solution, some are moving into the solution at a given time. And it turns out that if we have, more kind of gas molecules with enough energy to jump out of the solution, they're going to do that, right? We've already seen those graphs last semester about how increasing the temperature shifts the kinetic energy curve a little bit. I'll just draw it. This is way back when, here's your first temperature. You've got your velocities right there. And how about purple? When you increase the temperature, maybe now it's over there. You have your various kinetic energy here. You've got your proportion of molecules and kinetic energy. Those would be your various temperatures. We're going to see that the more temperature you give, or the higher temperature is, you'll have more kinetic energy. More kinetic energy means more likely to jump out of the solution. Things are going to be moving more quickly. Often these gases are nonpolar very often, like oxygen, carbon dioxide, what else? Nitrogen. All of these gases are nonpolar. They don't want to be with water, so we're giving them enough energy to kind of get out of there. They don't want to be there. We're letting them escape. So temperature is going to have kind of an inverse effect on solubility of gases. But as Kevin has said, if we increase the pressure, I shouldn't have drawn those graphs. Oh well. Let's copy this. Alrighty, so that's our kind of one pressure. I'm going to make this container smaller. If I do that, just the pressure here, that's going to force more particles to go into solution because they're going to be colliding more often. Remember that higher pressure means more collisions, right? That's how we look at pressure for gases. And then more collisions means it's more likely to go into our solution here. So that's how you're going to pressurize your various liquids. If you're at the soda factory or the beer factory or whatever, if you want to carbonate something, putting carbon dioxide inside, you're going to do that at pretty high pressures. So you're going to be forcing carbon dioxide to go into your solution by putting it in at high pressure. So the more collisions you have, the more gas particles can enter the solution, and they're just going to be kind of forced to stay there, right? So we can do that. This is a fun thing called Henry's Law. Which shows us that the solubility is related to the pressure via a constant. This is probably not an equation we're ever going to do anything with, but here it is anyway. This is the pressure. Technically, it's the partial pressure of whatever gas you're looking at. So if it's carbon dioxide or nitrogen or oxygen or whatever, that's what it's going to be. And K here is just going to be a constant that depends on temperature and your gas identity. So we're going to see temperature will affect this constant as well. You know, if your gas is carbon dioxide or ammonia, you know, those are very different gases chemically speaking. Ammonia is pretty polar. Carbon dioxide's non-polar. So we're going to see that, the amount that we can dissolve in our solution will depend on the identity of gas, and that will be accounted for in your constant. Again, this is not really something we're ever going to do math with, but just understand that the higher pressure we have, the more we're able to dissolve. Again, we're forcing collisions with the fluid interface there, the gas-liquid interface. Forcing more of those collisions means we're going to get more of those to go in there. And again, we're going to be more likely to break solvent-solvent interactions with higher temperature and to break solute-solute interactions as well. So, cool. That is our solubility stuff. Any questions so far? So what you need to know for this is kind of just these kind of relationships. So P is pressure. Sorry, it's partial pressure. I'll make this neater. So when we're looking at the pressure of one gas, we call it the partial pressure, right? Because often gases are mixtures of gases. So that will be the partial pressure of the gas. So if we're looking at carbon dioxide, it would be whatever the partial pressure of carbon dioxide is in our gas that we are putting into our solution. Okay. Cool. Alrighty. Let's have some more terms, because we love terms. So we've talked about solids and gases interacting together, how we can get those to dissolve. What about liquids? How do we get liquids to dissolve in other liquids? Well, technically solutions can be all sorts of different states of matter. You can have solids dissolved in gases. You know, you could have gases dissolved in solids. You could have gases dissolved in liquids. You know, typically we think of the solvent as a liquid, but technically your solvent can be any state of matter. We have special terms for these. We're going to have miscible versus soluble versus immiscible. Ew, that's really awful. Let me fix that. So we've got three terms to look at here when we're looking at liquids together. If a liquid is miscible with another liquid, that means it will always mix, no matter what the proportion is. So for example, ethanol and water are miscible liquids. No matter how much ethanol you put into the water, they will always mix perfectly. Whether it is, 75% ethanol and 25% water, or 50-50, or 10% ethanol and 90% water, it'll always mix completely. There's no kind of limit to how much you can have to mix them. Immiscible liquids will never mix. without outside help. That would be something like water and gasoline. If you try and put those together, they are not going to mix. If you have them both, they're going to form little layers like oil and water would. You can try and shake them up. They'll just separate out again. They're not going to mix. And so we're going to see that there's kind of these kind of two extremes. You've got miscible liquids that will always mix together no matter what, and you've got immiscible liquids that will never mix no matter what. And then kind of in the middle, you have ones that are considered soluble. And soluble liquids will dissolve to a limit. So eventually you will... Yes. And so the reason that the liquids might be miscible is because they would have similar intermolecular forces. And we'll talk about that in just a second. So something that would be soluble in water, for example, would be something like ethyl acetate. That's a nail polish remover, for example. You have several different types of nail polish remover, but that's one of them. If you take like 1 drop of nail polish remover, you can dissolve that in water. But if you put, try and make a 50-50 mixture, you're not going to get them to mix. And so you're going to be able to dissolve a little bit, but not that much. So there will be a limit to how much you can dissolve. So immiscible liquids, you will pretty much get no dissolving at all. Soluble liquids, you'll get some dissolving. And then miscible liquids, you'll get complete dissolving. So no matter how much you put in. And all of this, as Kevin has already said, because he's going to be the new instructor, all of these depend on intermolecular forces. So we know that like dissolves like. So something like water and formaldehyde are going to be miscible together because they both have similar properties. They're both polar. In the case of formaldehyde, we do not have hydrogen bonding. I'm sorry, I forgot to put a carbon for you guys. I'm thinking OChem already. There's our formaldehyde. Forget it. Let's keep it. We're going to have dipole-dipole interactions there. Polar interactions that can nicely mix these two together. So these are both polar, for example. Or as Kevin said, we had ethanol. I'm sorry, I'm again in my OChem phase. I'm sorry, these are really ugly. There we go. These would both have hydrogen bonding, and they're also polar, of course, so we would be able to see similar forces between them. We would expect them to dissolve together, to be miscible. So, our formaldehyde and our water will always be able to dissolve together. Our ethanol and our water will always be able to dissolve. However, if we take our water molecule and put it with let's put a hexane in there. Something you can find in gasoline. That would be not going to work, right? That would be immiscible. Both of these previous examples would be ones that are miscible together. But this one would be immiscible, right? We have hydrogen bonding, a very polar molecule with water, or something that is completely non-polar with hexane there. So those two are not going to mix. Those would be immiscible liquids. So they're not going to mix together. If you try and put your gasoline in water, you're going to see that it's just going to float on the top. It's less dense. It's just going to float there. It's not going to mix, right? Where something, however, like this, our water if we throw an OH group onto this hexane molecule, make it hexanol, this one will probably be soluble. For example, because it's got a huge nonpolar component, but it also has a bit that can do hydrogen bonding. So we're going to see that this is kind of like intermediate, right? It's probably not going to dissolve fully in the water, like to the extent that ethanol would, because we got this long nonpolar carbon tail on it. But because of that, OH would probably mix. And let's go ahead and check Wikipedia to see exactly how much that hexanol would dissolve in water. Hexanol solubility in water. It can dissolve about 6 grams per liter. So that's not a huge amount that can dissolve in the water. For example, if we look at sodium chloride, let's look at its solubility in water. We can dissolve 360 grams per liter. So that is 60 times the solubility difference there. So that's kind of what we're looking at. Generally, something we consider soluble to be roughly, we want that to be greater than 1 gram per liter. So for our kind of, sorry, creature is snoring, it's distracting me. For something with like these carbon chains, around octanol is where we stop getting water to be soluble with that alcohol, because at that point we will have solubility that is less than 1 gram per liter. So that's kind of what we're looking at number-wise. So something that's immiscible, we're looking to be less than 1 gram per liter. In fact, let's go ahead and look it up right now. Hexane. Let's see what its solubility is. 9.5 milligrams per liter. So that is way less than 1 gram, so we're going to consider that to be immiscible. And then for the ethanol or formaldehyde, we're going to see that we're going to have no limit. As many grams per liter as we want. There's no limit there. All right, cool. Any questions on those? I'm not going to ask you to like kind of necessarily predict one. I'm trying to make them pretty obvious. Like, you should be able to identify that something like this hydrocarbon should be immiscible with water. But I'm not going to necessarily ask you without giving you numbers to compare soluble versus miscible ones. So I'll, as always, try to make this as easy as I can for you guys. Alrighty, so I guess that's as much as we're going to do today, because I just wanted to go through the rest of the class stuff with you guys, just in case you did not watch the welcome video, which is, I guess, on you, but whatever. We're going to now have the same thing that we did last semester. We're going to have our participation for the first 2 weeks. And eventually I will update this silly tablet so it stops yelling at me to update it. We're going to answer the following, or do the following 3 things. You're going to introduce yourself. Actually, yeah, we'll do this. Where did you take 111 for anyone who's not taken me before? That's Gen Chem 1. We're in Gen Chem 2 now, obviously. So just curious if you have taken it elsewhere. I'm just curious. And then I'm here, and then 2B. If not, at Saracoso. Just kind of what topics did you cover, if you remember, in that class, just to make sure we're kind of all in the same boat here. And then 3, what do you do for fun? just something to kind of build camaraderie here. So I'll leave these up for a second. But if we go in Discord, we're going to go ahead and go to our general channel. I will answer these questions myself. And then you can kind of see what I'm doing. And then let's see, what do I do for fun? This is kind of what I do. So there you have it. That's what I'm looking for. So for those of you who have had my class before, this is not going to be anything new. You did this exact same thing last time. But if you are new, I will show you what to do real quick. I'm going to just pop over to Discord for a second just so we can see it. So you should be, when you're first entering the course, you're going to see this. When you click the link in Canvas, you're going to see that it'll take you to this page. For this class, we are going to want to click that little chick there. Ta-da! And that'll give you access to this class's channels. From there, you're going to scroll down to it. You're not going to see all this other stuff because you're in the 113 group. You're going to click this general tab here, and that's where you're going to be typing out all this fun stuff. So, who's calling me? How dare they? So that's where we're going to be putting this stuff. So as you can see, you have my answers up there, and then all of you can put your answers as well. Just again, this is an online course, so it is asynchronous, meaning there is no problem if you cannot make it to the live streams. And so you'll just be kind of, doing your own thing at your own pace. Things are going to be due usually on Sundays. Sometimes they'll be due on Saturdays if you have an exam the following week. I'll try and give you, a bunch of time to do that. But yeah, like this sort of participation thing, like try and do it by Sunday. Obviously, a lot of you doing it right now, which is awesome. Because why not? We have the time. And yeah, so cool. Of course, if you have any questions at any time, for those of you who have taken time with me before, you know that I am very quick at answering things on Discord. So that's going to be the best way to contact me. Just type something out here. I will see it. I will answer it when I can. So yeah. Oh, awesome, Laura. You live in LA. What part of LA do you live in? When I'm in LA, I live in Glendale. Though right now I'm in Ridgecrest, dealing with the wind and fun stuff like that, and planes taking off. And then for those of you who are new, you are free, of course, you can ask me whatever the heck you want as well. If you want to know anything about me, I'm happy to answer that as well, just to kind of connect us more when we're not in person due to horrible viruses. So, but yeah, so I'm happy to talk about whatever. So I've been pretty good. I enjoyed my time off. I only, remembered last week that we were about to start. So when I was teaching at another college, they had a winter kind of like 6-week session, so they didn't start spring until February. And I was like, oh crap, I have to start in January. So yes, as always. So we are on chapter 13 in the book. So here it is. We are on chapter 13 right now. Let's see, how far are we in chapter 13? It is a gaming chair. Secret lab, yeah. The most comfy things ever, right? So, it is important that we have this. So, we have technically covered sections 13.1, 13.2, and 13.3. So we are definitely going to be following the textbook here. So on the syllabus, you can see all the chapters that we're going through and kind of the rough idea of how much time we're going to be spending on each one. Wait a second. Oh, I think that's from a different classic. That's why that popped up there. But yeah, we're going to be following this pretty closely, simply because this is not my favorite class to teach. This is almost all physical chemistry, which is my least favorite type of chemistry. So I kind of lack the creativity that I would have otherwise in like OChem or something, where I have much more kind of comfort with the subject material. So kinetics I particularly hate. So that one we're going to pretty much be following the textbook exactly for the kinetics chapter. But some of the acid-based stuff I'll be having more fun with, just because I like those a little bit more. But yeah, we'll be going with the textbook. Just so you know, if you Google stuff, perhaps something like this, you may be able to find the 12th edition. But that's all I'm going to say. That's that. Don't worry, I'm sure the subject matter is the same. It's probably just changing the questions and throwing the word "and" in randomly or something, or rearranging something slightly. But yeah, older editions are totally okay to use. For your homework, when I do give you questions from the textbook, I'll be posting those on Canvas, the questions directly, so you don't actually need the textbook for that, so you are free to use whatever you like. But it is the same textbook as last semester too, so hopefully it'll be the same. I don't even know who these people are. And your puppy's name is Thanos. How lovely. I also eat for fun, which is, I guess, a too common thing in COVID, right? We've all got our COVID-15 now that we are always working on, so... Well, awesome. Believe it or not, Kevin, some people do like PChem. They do PhDs in it, and it's just awful, and I can't imagine doing that, but there are people who are kind of masochists in that way, so yeah. But we'll see. So at least this first chapter, thankfully there's not too much crazy stuff going on. It's a pretty short chapter. Thanos is perhaps a Greek name, but I think it's more the Marvel character, the Marvel Titan, right? We need to get Jackson out to watch the Avengers series, apparently, or get him into some comic books. So that'll be your homework, Jackson, okay? Go on to Disney Plus and watch all the Marvel stuff. I think Thanatos is the god of death, no? Let's find out. To Wikipedia we go. Yeah, it's Thanatos is death. So I do pride myself that I am occasionally able to be smarter than Kevin in certain random things. Yes. One more thing. For those of you who are interested in the honors section of the course, you can get an extra unit for it. You can get 6 units instead of 5 for basically 1 more hour per week. We would be doing Thursdays at 11:30 in Discord, where we would be doing that. For the honors section, the only difference is you do everything else the same, except once per week we do harder questions. And so... if you are interested in kind of going into stuff in more detail, let me know. I'll get you the permission slip thingy to switch you over to the honors course if you want. Depending on how many people in there, that's kind of going to determine how we do the course. So the more people we have, kind of the fewer problems you'll end up doing. Just because how I plan to do that is to have it kind of be, I give you guys like problems to do, and you would present them to each other. And these problems would be kind of just more in-depth ones. So, like on your exams, you've had me before. Like you've seen my exam questions and how they are typically easier than the questions we do in class. And so for the honors section, you would be basically given the types of questions that I would do in class, but without me doing them, and you would just do them yourselves, without much guidance there, and you would either be presenting them or just submitting them to me, depending on what we do. So if you are interested, let me know, and I'll get you in. But other than that, yeah, we're good. So that's it for today. Tomorrow we'll continue on with our solution excursions. We'll be finally doing a little bit of math at least. Our unit conversions will always be back. Okay, Carlos, I will go ahead and actually on Canvas there is a let's just see. Let me bring up Canvas here. Oh my gosh, I have so many tabs open. Is this the one? Yes. Oops, we don't need to see that. Go here. Aha! On Canvas, when you log into Canvas, there's a form here. You just download it. Really, all I need is your name and ID number. Like, just kind of fill out this top stuff and your like signature. You could just type it if you want, and then email it back to me. I can put in the course number here and then do my signature, and then I submit it to whoever the heck it is, and they will automatically swap you over to the honors course. So yeah, just get this and then email it to me, send it through Canvas or Discord, whatever. Do that, and then I can swap you over. What was I gonna say? Oh, you can also direct message it to me if you've used thingy before. What is this? Discord. You can click my name and message me. While this is technically Lorraine's name, because I can't click myself because I can't message myself, you can message me directly through this as well, and you can send it to me there if that's the way you want to do it. So I am happy to accept papers whichever way you like. Alrighty. Yeah, Kevin, I didn't bother putting that stuff. I can, though, because for whatever reason they don't want to put the Canvas things together. So I've only thrown the syllabus there. However, if you want, I can copy all that stuff. Though once you're on Discord, you should have it all there. But yeah, I'll go ahead and I'll copy that stuff over. I guess it would be useful to have. So, but it's silly. I can't like easily just copy it since it's silly. Well, maybe I can. Let's see. Okay, let's see. Select the content, modules, files, course settings. Yes, let's do that. Let's see if I can't get this to work, Kevin. Otherwise, I'll do it manually. Hooray! We kind of have that stuff there. Okay, Kevin. Now it should all be. It should all be there. Let me just delete this then. Oh, hooray! Okay. Awesome. Okay. Well, that's it for today. I'll see you guys tomorrow. We'll continue our solution fun. If you are watching this later, I guess I'm kind of preaching to the choir, but just go ahead and do your Discord thing afterwards. And that's that. So I will also, just so you know, be posting your lecture notes. So I always post those in Discord for you guys just because the tablet is not able to upload them to Canvas directly, and I'm lazy and don't want to like email it and deal with that. So it's easy to have it here. Have to find the right one. Ah, that's the one for us. So you'll have those in Canvas or Discord as well. So if you look at our tabs here, there is a tab that you should not be able to write in, but that's where you can download the notes from for that day. So there we have it. See you guys tomorrow.